Okay, so a couple things we're going to go over that we're going to use pretty much in every um, part of problem solving in physics is scientific notation, significant digits, rounding based on significant digits, and unit conversions. So let's start with scientific notation. We use scientific notation whenever we have a very, very large number or a very, very, very small number. For example, instead of having to write 100 digits, it's a lot easier to write times 10 to the power of something like 99. And so scientific notation, how we write it is, we always start with a non-zero digit, and then a decimal, and then whatever digits remain in our number. And then we multiply that by a factor of 10. So for example, this number, the decimal's over here, but I'm going to move it all the way over to there. So I'm going to write it as 3.674892 and multiply that by a factor of 10. To what power? Well, you just count how many places you move the decimal over. In this case, 1, 2, 3, 4, 5, 6 places. So times 10 to the power of 6. For this one, we'd need to move the decimal place over to the right. 1, 2, 3, 4 places. So I'm going to write it as 2, so a non-zero digit, decimal, and then the rest, 5, 3, 6, 5. And since I moved the decimal 4 places to the right, we're going to give this a negative exponent, like this. So next thing we're going to talk about is significant digits. Significant digits is very important in any science, really. It tells you the accuracy of your measurement or your calculation. So I'm sure at some point everyone has put in a calculation in maybe their math class or science class, and on their calculator they get a huge long number, and you raise your hand, you say, like, how many digits you want me to round to? Well, there's actually rules for that. And it is based on accuracy. So here I have a ruler. Now let's say I have a line, just a straight line from here to here. And I wanted to measure the length of that line. I might look at the line and say it's 5.6, 5.7, maybe somewhere in between there. Let me go with 5.65. There you go. So what did I technically do here? I knew it was somewhere between 5.6 and 5.7. So this digit here, I really just estimated. Could have been 5.64, right? Or 5.642, or who knows, right? This tells you the accuracy, right? These two digits, I know. The next one I estimated. But now imagine you have a ruler that doesn't have these little millimeter marks. So let's say it just has 0, 1, just the centimeter marks. In that case, it would have been a lot more difficult. It would have kind of looked like it's right in between 5 and 6. So I might have just said, it's 5.5 centimeters. Notice the difference in these numbers? Even though I'm measuring the exact same thing, my measuring tool is different. In this case, I guessed the 5. Right, so that last digit is my estimated digit. So if I gave something to 2 students to measure, one student used this ruler, another student used this ruler, and they came up to me with their measurements, and this is something I want to use in my calculations for whatever lab I'm doing, this first one is the one I'm going to want because it's more accurate. It has more what we call significant digits. So what are significant digits? Well, they measure accuracy. And how do we tell if something is significant? Here are our rules, these 5 rules. 1, all non-zero digits are significant. So for example, in this number here, we can count 1, 2, 3, 4, 5. There's 5 digits that are non-zero. So in that number, we have 5 significant digits. Next rule. All zeros between two non-zero digits are significant. So these two zeros, which are between 4 and 3, which are non-zeros, are significant. So this would have 4 significant digits. Next rule. Zeros which are only used to fix a decimal position are not significant. What does that mean? Well, this 0.00, those don't have any meaning other than the position, or the multiple by 10 if you want to look at it in scientific notation. The important part here is just that 5 and 2. So this one only has 2 significant digits. However, zeros after a decimal point to the right of the non-zero are significant, right? I mean, I could have gone here and said it looks like it's right on 5.6. So I'm going to say 5.60. I'm pretty certain about that. Well, that 0 counts right there. It tells you a bit about the accuracy. So in this case, this 0 counts, and in this case, that 0 counts. However, these ones, according to Rule 3, do not. So both of these situations, they each have 3 significant digits. And finally, rule number 5, something like this is honestly incorrect. If you were to write a number like this onto your lab report, then it's not correct because it doesn't tell anything about the accuracy. So what do I mean by that? The ultimate rule for scientific, for significant digits is, if you're not sure, put it in scientific notation. Because when it's in scientific notation, all digits count. So looking at this number, well, I could put it in scientific notation. I can write 5.2 times 10 to the, and then just 3, 6, 9, 10. 5.2 times 10 to the 10. But is it 5.2 times 10 to the 10? Or is it 5.20 times 10 to the 10? Or is it 5.200? I don't know. Writing a number like this says nothing about the accuracy. So in a proper scientific report, you'd never see a number like this. And if you do see a number like that, the only thing you can really do is assume the worst case scenario, that it only has 2 significant digits. Now, the thing that bothers me a little bit is your textbooks will sometimes use numbers like 320, and then based on the answers they give, you can tell that they're assuming that's 3 significant digits. It's just one of my little pet peeves that the textbook does, but just so you know. So now let's say, okay, we measured this length, and maybe we also want to measure, maybe it's a rectangle, and so it has a certain height to it, like that. I can measure the height to be something, maybe 5.8. So let's say one student measured it to this accuracy, but our other student over here measured the height to this accuracy. And I want to figure out the area of this rectangle. Well, how accurate is my calculations for the error? And that goes on to the next part. If I go up here, where are we going to round off? When I multiply those two numbers, where do I round off? Well, it turns out you have to look at your worst case scenario. If you have something that has 3 significant digits and you're multiplying it by something that has 2 significant digits, your calculation can only be as accurate as your weakest link, which would be 2 significant digits. Sorry, this guy keeps barking. So, this is our rule for rounding off. Let's look at these two numbers. I'm multiplying these numbers here. This one has 3 significant digits. and this one has 3 significant digits, meaning my answer should only have 3 significant digits. So if I just took a calculator and I did 2.67 times 10 to the 3 multiplied by 5.68 times 10 to the 29, well, my calculator says 1.51656. That's way too many. I don't need that many. I can only have 3. So I have to round off to 3, which would be 1.52 times 10 to the 33. Similarly, in this next example, this number has 3 significant digits, and this number has 4 significant digits. That here, that 3 significant digits, is my weakest link. So my answer should only have 3 significant digits. So again, if I put those on a calculator and multiplied them, you get 0.251121. But again, you have to round to 3 significant. Now that 0 is a placeholder, so it doesn't count. And 251. If you want, you can put it in scientific notation. You don't have to. It's not a hugely big or small number. But let me just... There is a couple of things I wanted to mention about this. Sometimes I'll get, say, a question, something as simple as, okay, 2 times 12. And students will look at it and say, well, that's 24. But if I can only write 1 significant digit, does that mean the answer is 2? Is 2 times 12 2? It's like, no. It's not 2. That is not how you would write it. But it is true. You can only write it with 1 significant digit. And how you would do that then is like this. 2 times 10. You would write it in scientific notation. So yes, you are rounding to 20, but you're certainly not rounding to 2. Also, depending what these numbers are, you might keep it as 24. Like, what is 2? If 2 is a measurement, then it only has 1 significant digit. But if 2 is a counting number, for example, there are 2 apples, 1, 2. You're 100% sure there's 2 apples. You didn't make any estimation in there at all. And so if you're counting something, that number would have an infinite number of significant digits. Right? So if these are counting numbers, so maybe you have 2 barrels, each with 12 apples in it, well, you counted 2 barrels, so that's an infinite number of significant digits. And you counted exactly 12 apples. There's no estimation there. So in that case, you don't have to round to this. You can leave it as 24. Okay. Last thing is, of course, unit conversions. Everything we do in physics has a unit. Right? It's not like maybe in math you might go 3 times 5 is 15. In physics it'll be like 3 what? 5 what? And that equals 15 what? Like centimeters, meters per second, liters, like volume, like everything we do calculations on has some meaning in the real world, and therefore is some form of measurement and has some kind of units. And we'll always put something into what we call SI units, or standard international units. Okay, and the base is right here. And the great thing about SI units is everything is a power of 10. Right? So if your base for length would be meters, you could have kilometers, which is 1,000 meters, a megameter, which is 1,000,000 meters, or a gigameter, which is 1,000,000,000 meters. You can also go in the other direction, right? Hundredths, a thousandths, a millionth, or a billionth. Okay, and these are the symbols. Now I want to go over one of these in particularly that we use a lot, and that is this one here. So a lot of the times in the world we look at speed and we have sort of an understanding of what kilometers per hour is. It's because we're always in cars, right? So if I say something's moving at 100 kilometers per hour, you get a pretty good idea, oh, that's highway speeds. But if I said something's moving at 30 meters per second. It's like, how much is 30 meters per second? What would that be? But in physics, meters per second are the base units of length and time. And so all of our calculations are done in meters per second. So we need to know how to convert them back and forth. And this is the conversion we do most often. So let's start. I'm just going to do this down here. Start with 90 kilometers. I'm going to write it as a ratio like this, 90 kilometers per hour. So I have to convert kilometers into meters, and I have to convert hours into seconds. So let's start with kilometers. There are 1,000 meters in a kilometer. So what I can do is I can multiply this by a ratio that's equal to 1. I'm not changing anything. If I multiply anything by 1, it doesn't change. But it's not going to look like 1, because what I'm going to do is I'm going to write this, 1,000 over 1. Certainly doesn't look like 1, but if you include the units, 1,000 meters for every 1 kilometer, well, 1,000 meters is 1 kilometer, so that ratio is 1. But I can cancel the kilometers now, because we have 1 in the numerator, 1 in the denominator, they cancel. And therefore, if I just multiply those numbers, you get 90,000 meters per hour. Still not what we wanted, though. We wanted meters per second. So let's work with those hours. Well, we know there's 60 minutes per hour. So what I can do is I can do 1 hour per 60 minutes. And the reason why I do 1 over 60 instead of 60 over 1 is because I want these hours to cancel. I want there to be 1 hour in the numerator and 1 hour in the denominator, or else they're not going to cancel. And so now I'm left with meters per minute. I'm going to do it one more time to change it into seconds. So 1 minute per every 60 seconds. And now your minutes cancel, and we have meters per second. So all we have to do is take 90, multiply it by 1,000, and divide it by 60 times 60, which is 3,600. And that'll give me an answer in meters per second. To make it even more simple, 1,000 over 3,600 is the same as just doing 90 divided by 3.6. In our case, if you do 90 divided by 3.6, you get 25. So that is 25 meters per second. All right, so moving on to our first lesson. This is our Unit 1 kinematics, Lesson 1, position, motion, and displacement. So there's a lot of new terms we have to go over. The most important ones are, to start with anyways, scalar and vector. So there's two different types of quantities we're going to analyze in physics, mathematically. One's a scalar quantity and one's a vector quantity. Now, scalar quantities you've used for a long time. You just didn't realize they were called scalar quantities. Any measurement that has some magnitude is a scalar quantity, like 5 meters. But when you add a direction to that magnitude, like 25 meters east, it becomes a vector quantity. So a scalar quantity has magnitude but no direction, and a vector quantity has both direction and magnitude. And so time, for example, 6 seconds, 5 hours, that's a scalar quantity. Speed, say on a highway, 100 kilometers per hour north, that's a vector quantity. Now to start with motion, we have to look at a couple terms, and we have to understand whether or not these terms are scalar or vector quantities. First one is position. Position says where you are relative to a reference point. Okay, so let's look over here at this hockey player. And let's say the center of the rink is the origin. Well, it looks like this person is 5 meters. Let me just add a little coordinate system. There's north. So he's 5 meters east of the coordinate system. That's a position. Right? Notice that there's a direction. East, south, west. Notice there's a direction. I can't just say 5 meters because then he can be anywhere along that radius around the origin. To be specific about where this hockey player is, I have to say a direction as well in order to identify their position. So position is a vector quantity. Now let's say that this hockey player moved from this position here, which would have been here in this diagram, all the way over to this position here. So our initial position would have been 5 meters east, but after moving, we moved to a position of 25 meters east. Now there's two ways to describe that motion. We can simply say, well, how far did they travel? Well, 20 meters. And that's called distance. Distance is a scalar quantity, and it doesn't matter what direction. So this hockey player could have gone up, down, left, right, doesn't matter. Right? Well, technically not up, that would be jumping. North, south, east, west. Doesn't matter. You can quantify their distance using just a magnitude. However, if you want to be specific, then we're going to use something called displacement. Now, displacement is a vector quantity. In this case, you go from 5 meters east to 25 meters east. So you moved a total of 20 meters to the east. And if you're specifying direction there, then that is displacement. Displacement is referred to as change of position. And we can write it down as a formula right here. This delta symbol means a change. And then we have D, but we also have this little arrow above the D. Anytime we put an arrow above a variable, that represents that that variable is a vector quantity. Okay, so our change in D, here we have D subscript F, that F stands for final, so final position. Notice that there's an arrow above it to represent that position is a vector quantity. And then we subtract our initial position. That's what the I stands for. So if we have final position minus initial position, anytime you do final minus initial, that represents a change. And a change in position is displacement. So what this equation says is that displacement is our final position minus our initial position. So let's look at this example. If I were to write this out mathematically, I mean, it's easy to tell just by looking at it. Going from 5 meters east to 25 meters east, we moved 20 meters east. But writing it out as an equation, our final position is 25 meters east. Subtract our initial position, which is 5 meters east. You can see it works and gives us exactly what we thought it would be, 20 meters east. Now there's one other equation I wrote here, and that's total displacement. So this could be in the situation if you start here and move here, and then you move back here, then you move over there, then over here, and then over here, right? If you add all of those displacements up, you would get your total displacement. Could have moved in the west direction. What would we have done then? Well, we do have a convention. We usually, if something's moving in the east, we can give it a positive value. And if something's moving in the opposite direction, we give it a negative value. What does that mean? Let's say we're to draw a vector here. A vector we usually just draw as an arrow with a certain length. The arrow represents the direction and the length represents the magnitude. So if I had, say, 10 meters and I wanted to add 5 meters, Well, that just equals this vector here, which would be 15 meters. But what if I didn't keep walking in the same direction? What if I had 10 meters and then I turned around and walked 5 meters? Well, if I add these two vectors, you end up with this, right? We start here, go here, and then come back here. So if you compare your starting point with your finish point, what you've essentially done is you've gone from here to here. Okay, so if this is 10 and this is 5, what I'd have to do is, it would seem like I have to add them, because that's what the equation is. Total distance is the sum of all other, total displacement is the sum of all other displacements. But taking 5 meters east and adding 5 meters west, it looks like 10 plus 5 is not 5. I mean, it looks like, based on my diagram, you should get 5. That makes sense. But 10 plus 5 is 15. And here's the problem. When you're adding them algebraically, if they're not in the same direction, you cannot simply add them. What you have to do is realize that, say, you have this vector, which is 5 meters west. That is the exact same as simply taking the negative and changing the sign to the opposite direction. Okay, we kind of call it anti-parallel. So these two lines, they're parallel, but they're in opposite directions, right? Most people think anti-parallel means perpendicular, but it doesn't. Anti-parallel just means parallel, but opposite directions. And in order to do that, we flip the sign of both the direction and the negative in front. So I can add these if I simply change that positive 5 meters west to negative 5 meters east. Now that the directions are the same, 10 minus 5 is 5 meters east, which gives us exactly what we would think we would get based on this diagram. Okay, and so this is a convention. Right? You don't always have to use this convention. You can use any convention you want, really, as long as you're consistent with it. So east is usually positive, up or north is usually positive, right is usually positive. So let's go over an example. So in this example, here we have a traveler initially standing 1.5 meters to the right. So here's our initial position of the Inukshuk, right there. And then moves so that she is 3.5 meters to the left. So here's our final position. Determine the traveler's displacement algebraically. Now we can use directions or we can use our convention with signs. Let's do one of each so you can see the difference. So if I use directions, well, the equation is final minus initial. My final position is 3.5 meters left minus my initial position, which is 1.5 meters right. Now I can't add left and right, so what I need to do is change this to positive and then change the sign to left. So this just becomes 3.5 plus 1.5, which is 5.0 meters left. Which makes sense if we started from here and then we moved from there all the way over to there. We moved 5 meters left. Now, what does it mean by using plus or minus signs? Didn't we just use plus or minus signs? Well, no. This is sort of just an easier way, a lot messy way. So what we do is we say, okay, right is positive. So we sort of show what direction we're going to use as positive, and then we go displacement, same equation, is final minus initial. And then we just look. So d final is 5 meters left. Oh, left is not positive. So I'm going to write that as minus 5 meters. And notice I'm not writing a direction here. The direction is right there inside of that negative. That negative with this coordinate system shows the direction. And then I would subtract our initial position, which is 1.5 meters right. Right is our positive direction. So that's positive 1.5 meters. Now if I do this, oh, this isn't, sorry. Initial final position was not 5 meters, it was 3.5. Let me just fix that. Now if I do that, you get minus 3.5 minus 1.5, which is minus 5 meters. Now you might say, how are these two answers the same? Because they should be. In physics, if you're doing something correctly, no matter what way you do it, you should end up at the same destination. And remember I told you the sign represents the direction. So this is a negative. But according to our coordinate system, negative is to the left. So that negative means we can rewrite this as 5 meters. And we can pull that negative out and write it as our directional component. So you can see they're both the same. Now what we're going to be doing in this course is I am going to mostly be using that second method, because it is the convention that is mostly used in physics. But I would recommend you start with the first method, because vectors are still new to everybody, and then slowly move towards the second method. Okay? Alright, so this next question, we're going to look at graphs. I'm first going to start introducing you different graphs, and we're going to start with a position time graph. Okay, now it's very important that it's position time graph. I know the grade 9 math textbooks call them distance time graphs, but that's not right. Now that you know the definitions, you know there's a difference between distance and position. Position is a vector, distance is a scalar, right? And it's important we look at the direction if we're going to actually analyze where someone is at a certain time. So here we have two rollerbladers, A and B. They're having a race. B gives A a head start of 5 seconds. So you can see B, which is blue, starts moving over here at a time 5 seconds, and A starts moving right away. Each rollerblader moves with a uniform motion. Uniform means unchanging or constant. It means their speed is the same. And if their speed is the same, that just looks like a straight line. If it's a horizontal line, it means their position isn't changing. And if we have a horizontal line at 40, well, it's remaining at 40, so that person's not moving anywhere. But if it's a diagonal line, it means they're moving, but they're moving with a constant speed, so unchanging speed. Assume that the time taken to reach uniform motion is negligible. So what that means, if you start running, it takes a certain amount of time to get up to speed. So we're just going to ignore that. If A travels 100 meters in 20 seconds, so at about 100 meters, which is here, at about 20 seconds. So we just plot our second point and connect it to our first point in a straight line because it's uniform motion. And B travels 112.5 meters in 15 seconds. So at 20 seconds, the reason why we do 20 is because that's 15 seconds after they started. They moved a total of 112. So we put a mark right there, 112, and then connect them. And then it says, Find the time, position, and displacement which B catches up with A. So B catches up with A right here where the lines intersect. At that point, their positions are the same. And it happens right here at 15 seconds. And right here just under 80 meters. Okay, so we're not going to come up with an exact answer. We'll learn about the algebra a little bit more later. But for now, I want you to understand a position time graph and how it looks. And we are going to do more work with position time graphs over the next week or two. Now, the last question says, person walks 10 meters forward. Okay, then 3 meters forward, and finally 8 meters backwards. Find the total displacement. Right, so our total displacement is just the sum of all the other displacements. Delta D1 plus delta D2 plus delta D3. So what we have here are 3 meters forward. Oh, sorry, first is 10 meters. 10 meters forward plus 3 meters forward plus 8 meters backwards. However, that 8 meters backwards, I need to do something because I can't add forward, forward, and backwards. So what I need to do is, in order to change it to forward, I need to take the opposite sign. So that leaves us with 10 plus 3, which is 13, minus 8, which is 5 meters forward.